All right, here we're going to talk about linear regression and correlation. This corresponds to chapter 12. Basically, here, this is different types of testing. So far, we tested for population mean, population proportion. We also tested if two variables are independent. Here, we want to test if two variables are correlated or two variables are related in certain ways. For example, I want to see if number of hours you study is somehow related to the score you get on the exam, or number of times you're absent during the semester corresponds to the number of points you get on the exam. So I'm comparing two quantitative data set, two numbers, to see if one variable kind of affects or is related to the other variable. So we want to determine if there is a correlation between two quantitative variables. We can't really do correlation with qualitative variable. We have to be number versus number, right? So the data collected comes as a pair, ordered pair. So we're going to see two corresponding numbers together. So one is matching the other number. We use the variable x to represent the independent variable, independent. But I think it makes more sense to refer to it as explanatory variable, and the y variable is dependent. Or I think it makes more sense to call it response variable. So the independent variable basically affects, we're trying to say independent variable, the explanatory variable affects the response variable. So I want to say in the explanatory variable causes response variable to respond to some certain things. Okay, so we say x and y are linearly correlated if a linear relationship exists between two variables. So we're going to kind of look at the graph. If the graph of order pair on a scatter plot is point appear to be a straight line, it's called linear correlation because if we draw the graph of it, it should look kind of like straight line. So if data forms kind of like a straight line, then there's a really linear correlation. If data is just random points, then we say there's no linear correlation. How to create a scatter plot on your calculator? We're going to actually use Google Sheet. Basically, once you have data on the sheet, you use insert function key to go to chart. That will get you a scatter plot. All right, let's look at the next part here. The linear correlation coefficient R measures the strength of linear relationship between the pair value. I think we can just stop here. It has, so basically, but in real life, instead of looking at the graph to see they form a linear, like a straight line, to see if there's a correlation, what we're going to do is we're going to calculate this number R to see if there's a linear correlation. This number is called linear correlation coefficient. And then what we're going to do is we're going to compare that number to the critical value to see if two variables are correlated or not. So how do I calculate this R linear correlation coefficient with your calculator? First, obviously, it's input x values in L1, input x values, so y values in L2. Then we kind of go to tests. So we've done that before. We did a bunch of different testing. If you scroll down, option F has a linear regression t-test. Sounds kind of long, but this will, when you enter, it gives you R. So once you calculate the R, first we'll talk about the property of the R, and then we'll decide, okay, when we get this number R, like how do I know by looking at it that two variables are correlated or not? So let's look at the property of R first. The value of R does not change if the values of either variables are converted to different units. This is a minor point, but if you're measuring somebody's height in inches versus feet versus centimeters, if they're correlated, they're correlated. It doesn't matter what you're measuring in, what unit you're measuring it in. Second one, it says the value of R is not affected by the choice of x and y. Interchange of interchanged all x's and y values, and will not change, right? So if x is correlated to the y values, then y is also correlated to the x values. So it doesn't matter if you switch x and y. R measures strengths of a linear relationship. We're not going to talk about it in this class, but some variables are related, not by straight line, but they form like a curve. So sometimes maybe it's quadratic, maybe it's parabola. So linear is the easiest one, but maybe there's some relationship they form like a curve instead of a straight line. So we're not going to talk about that, but R just measures a linear correlation, linear relationship. That's it. Okay, so first, how do I, using R to determine if there is correlation or not. So decide if the significance level is 0.5 or 0. Again, this is the default one, right? So unless it says use 0.1, we'll use 0.5. So compare the absolute value of R to the critical values in the table. So table is given here, right? Table is at the end of the page too, but this gives you the critical value. So maybe I should write that. Critical values table here. So we're going to compare what we calculated from the calculator to the values in the table, basically. So come back to number 6 here. If the absolute value is bigger than the critical value, there's a correlation. If absolute value R is less than the critical value, there's no correlation. I guess you can put equal sign there too. I think it's easier to look at it graphically. So here, I'm going to make another comment. When you calculate the R from the calculator, all your answer is going to be between -1 and 1. So R is going to be between -1 and 1. So it doesn't matter what kind of data you input, R is going to be always between -1 to 1. It could be 0, it could be -9.99, but it never be 1.2 or anything like that. So graphically, this is how it's going to look. Here's a 0, here's -1, here's 1. So critical value. Again, critical values depends on your sample size 4 through 100, and your alpha, most likely 0.05. So 0.95, 0.666, whatever. These are all different critical values, right? So critical value is going to be something. In the table, it only gives you positive, but you can just think of it as a positive and negative. So graphically, this part is correlated. This part is correlated. And anything in the middle is not correlated, right? So not correlated. So whatever you calculate from the calculator, if it falls in between critical value and -1, that means your data is correlated. If it falls in here, that means your data is correlated. If it falls in here, then your data is not correlated. So this is how I can tell if my data is correlated or not, by looking at where does the number I calculate from the calculator, where does it fall into? Here, here, or here. So this is what basically it says. All right, so using R to determine if there's a correlation. Basically, we kind of talked about it, but if I were to do it a little bit more formally by using hypothesis testing step. So hypothesis testing for linear correlation is going to be slightly different than normal process of hypothesis testing. Instead of looking at the p-value, we're going to look at R and just compare it. So number 7, using R to determine if there's a correlation. The population correlation is called this thing, rho. It looks kind of like P, but it's pronounced rho, R-O-H, is the equivalent of R. The null hypothesis is always going to be rho is equal to 0. And an alternative hypothesis is going to be rho is not equal to 0. So these are basically fixed. Which means for every hypothesis testing for linear correlation, H0 and H is going to be always like this. H0 rho is equal to 0. This means no correlation. Not 0 means there is correlation. Right? This is kind of like what I talk about in the graph. If your correlation coefficient is close to 0 is not correlated. If it's not close to 0, meaning close to -1 and 1, is correlated. All right, calculated function key used. Here, you don't have to worry too much about this part. Calculated function key used, again, linear regression t-test. So here, if you reject the null hypothesis, that means you're rejecting the fact there's no correlation. That means you're supporting HA. That means support HA. That means there is linear correlation, because HA says that there is a correlation. All right, maybe we can look at, we're gonna fast forward to one of the questions here, and then we'll come back. I wanna just do one example. Let's look at number 14. So data in the table shows the age and the number of siblings of 10 sample PCC students. So this person is 49 years old, 7 siblings, oh, that's a lot. 46, 9 siblings, 21, 3 siblings, 20, 0 siblings. So I want to see if the age somehow affects or influences number of siblings. So is there a significant correlation between age and number of siblings at 0.05? So if we were to kind of write down H naught and HA, rho is equal to 0, rho is not equal to 0. So there's a correlation, no correlation, and there's correlation. Again, as I say, instead of doing our usual p-value, here we're going to calculate R to see if there's a correlation or not. Again, I'm going to draw the graph. There's -1, there's 1, there's 0. Here we have 1, 2, 3, 4. There are 10 sample PCC students. So let's go down. There's another chart at the bottom of the. It's 10 right here. Let's see, n is 10. Alpha will pick 0.05. So critical value is 0.633. So again, 10 people, my sample size, 0.632. So let me come here, 0.632, 0.632, negative 0.632. So basically, this part will be, this is correlated, in the middle is not correlated. So this will be my setup. So what I'm going to do is I'm going to plug these numbers into the calculator, and I'm going to calculate the number R from this data set. So if R from the data set falls in here, then these two are correlated. If R from this data set falls in here, then no correlation, right? Let me write no correlation here. No. So what I'll do is I'll put it as L1, L2. So I'll put these numbers into L1. I'll put these numbers into L2. So once I plug in those numbers, I go again linear regression t-test, and then it'll ask for X list. I did L1, Y list, I did L2. It'll also ask for frequency. It's just gonna be 1. Here you don't have to worry about why is it 1. It's just gonna be 1, and our symbol is gonna be not equal to. That's just the HA symbol. So I'm gonna put that in. And it also asks for regression equation. You don't have to put anything there. Then once you enter calculate, oops, then it gives you a lot of different numbers. You scroll down a little bit, and like one of the last numbers you see is R squared at the bottom, and then there's R. So R is equal to 0.519. So my data gave us 0.519 as R value, which is like right here. It's not in the red region, it's in the middle, because 0.632 is here, 0.519 is like closer to 0. So let's see, this goes here. So no, not correlated then. So basically we failed to reject. So if I were to do it a little bit more formally, we failed to reject H naught, failed to support HA, so no correlation. So for this linear correlation, we're not going to follow like traditional like p-value hypothesis as conclusion. Here we can just say, oh, my R is here, so I can say there is no correlation. All right. Okay, let's go back to the example we were looking at here. So there we go. If we do have a correlation, then you can use the regression line. You remember the testing we did was called linear regression t-test, that regression. It's called the best line of fit or least square line to predict. So that line we're going to use to predict y value for given x value. So an equation of a line of the y is equal to a plus bx. You know that sometimes the b is called the slope, right? It's the one number that is attached to x. X is the intercept, y intercept, and b is the slope, right? You can think of this as straight starting. A is basically like a starting point, and b is the rate of change, which is the slope. Let's look at number 8. You can kind of work on it. You can skip it if you want to. You can. This is optional. If you wanna, like, if you like algebra, you can kind of do 8. Otherwise, you can skip 8. What we do is let's look at number 9. How to predict y value given x when there's significant correlations. So if there's correlation, it gives you an equation of the line. So how do I predict y value? Basically, we plug in x value into the equation to get y. So if I know x value, I can predict what the y value is going to be. So the example we looked at, the age of people versus how many siblings they have. Here we couldn't do that because they're not correlated, but for sake of argument, if these two things happen to be correlated, then basically what I can do is, I can tell me how old you are, then I can try to predict the number of siblings you have. And basically the calculator gives you an equation to do that also. All I have to do is plug in your age, and whatever I calculate, that's my best prediction for how many siblings you have. So that's what we're trying to say here. How to predict y values when x is given. I plug in x value into the equation to get y. What if there's not correlated? Then the best prediction is basically the average. So then how to predict y value when x is no significant correlation, then x means nothing basically. They're not even related. So basically use the average of all y values, right? Let's go back to the example we worked on. Sorry, we're going back and forth. But when you got your answer when r was 0.519, one of the first numbers, like 1, 2, 3, fourth line gives you a and b. A is 1.03, b is 0.11. So here it gives you the equation of the line. Not that we're going to use it because they're not correlated, so it's useless. But if I were to come up with the line, equation of the line, it'd be basically like this: 1.03 plus 0.11x. This will be the line. Because we're talking about the equation of the line, it's like, how do I even get that? When we calculate the correlation R, basically your calculator gets you the equation of the line as well. Again, if these two things are correlated, this is useful. Basically, I can input x, which is your age, then I can estimate or predict how many siblings you have. In this particular case, they're not correlated, so this is completely useless, but it's just there in case if they're correlated, I can use that. So let's go back to where we're here. So let's look at number 11. For given line of best fit, you computed that R is 0.6501 using n is equal to 12. And the critical value was 0.576. Can it be used to prediction y or not? So kind of like what we talked about. They said that the critical value is 0.576, so that's where you draw the line. 0.576, negative 0.576, correlated, core. Here, they say R was 0.651. So basically R is right here. That means they're correlated. So yes, correlated. So we can use the line. Can use the line for prediction. All right. Let's look at the next one here. So I'm gonna have you try number 12. And after you're done with number 12, let's look at number 13. It says data collected relationship between the number of hours per week practicing musical instrument and then score on the math test. Okay, interesting. They say, but however, there's a significant correlation. So they're correlated. Okay, that means I can use the line to predict what score you're gonna get by looking at how many hours you practice per week, right? So, okay, I'm thinking that because it says significant correlation. The best fit line, they give you the line. Okay, so I'll use that. What would you predict the score of math test would be for a student who practice a musical instrument for 5 hours? So this is my x value. Okay. So basically they're questioning like what would be the prediction for y value. Okay, so I'll use the equation 72.5 plus 2.8. I'll plug in 5 for x. So this example is 5 hours, but if somebody studies 7 hours, then I'm going to plug in 7 here. So whatever number I calculate there, that's what I predict this person to get on their math exam. So for this one, if we calculate this one out, I get 86.5. So that's my best prediction for this person who practiced 5 hours. I predict this person's math score is going to be 86.5. All right, number 14, we did the first part. Let's look at the second part of number 14. It says, predict the number of siblings for PCC students who's 25 years old. Again, because they're not correlated, this equation is meaningless because there are no correlation. So I'm just going to ignore that equation even though your calculator gives you that. So how do I calculate the number of siblings? How do I predict the number of siblings for this person who's 25 years old? Basically, I can ignore this, even this person is 25 because it doesn't influence how many siblings you're gonna get. Basically, find the average. Find the average of all y values. Okay. So here, let's look at the data again. I have number of siblings here, right? So basically, I'm gonna average these two. Fortunately, we already input this into L2. So basically I can do go to calculate 1 var statistics and L2. That'll get you the average. So 1 var statistics under calculate, right? Once you go there, it'll ask for the list. It's going to be L2. And the frequency is going to be nothing there, so just leave it blank. And then it'll calculate the average for you. Basically average, it gives you the x bar, but here I'm going to use y bar because it's y, so it's 4.9. So I can say average people have 4.9 siblings. All right, it's okay. And I'm going to have it finish number 15, and I think that's it. And just let you know there's another table down there too. Okay, so this concludes our worksheet here.